Hi, I'm Jill Rowley, and this is my Physics 2212 Lab 1. The background for today was that I examined common household objects and tried to figure out their excess charge or deficiency of charge, excess charge being electrons for negative charge. And specifically with tape, I evaluated its reaction with like charge tape and with other household objects in order to try to determine the amount of excess or deficient charge for the tape in the order of a magnitude of C, coulombs, which is the charge metric. Some applicable physics principles were electric fields. That's that concept that a positive charge has an electric field pointing outward and negative charge has an electric field pointing inward. And those are vector fields that are not determined by interactions with other charges within a field. Charge forces, this is dependent on other charges within a field. So two like charges will repel one another, two opposite charges will attract one another, and that's Coulomb's law. And gravitational forces also come into play depending on the way that these point charges are aligned with one another, and I'll get into that in a little bit. But to summarize the results from today, I found that the tape was positively charged, therefore electron deficient, and I also found that it was possible to identify that approximate amount of excess or deficient electrons on a specific piece of tape as a point charge in relation to its known surroundings, given the mass and distance to these known charged objects using the principles of physics that I'd outlined here. I also determined that electric force is equivalent to gravitational force when two like charged objects float one another. And I'll get into a diagram of that in a little bit. But some of the assumptions I had made were that these two pieces of tape would repel one another from the start because they have to have like charges. And so like charges are always repelling one another. But to determine what that charge was, I had to use other common household objects like a negatively charged pen. And when that was attracted to the piece of tape, I determined that the piece of tape had to be positively charged and therefore electron deficient. So in this floating tape scenario, there's a piece of tape B and there's a piece of tape A. And this is this diagram here. And with the piece of tape B, it's floating because the piece of tape A is the same charge. And so piece of tape B is being repelled by that. So net Y component of force on tape B is 0, given that that momentum of tape B is non-changing. In order to determine gravitational force on tape B, the mass of tape B is required. And so I took these initial data measurements and used these principles that I had outlined earlier, electric force specifically, and charge and gravitational force to determine how exactly the magnitude of charge was for this point charge piece of tape B. So assumptions I made. Each U-tape has to have the same net charge. This is because when I put each of the U-tapes next to one another, they were at an equidistant to one another. One was not overpowering the other. So I assume they had the same net charge. Each tape's charge is also located at a single point at the center of the tape. That's an assumption I made to ensure that free body diagrams were a little more simpler to read and that distance to a point charge is a little simpler to evaluate. So I found here with the system of point charge B and the surrounding of point charge A, I outlined that the force of the electric charge was pointing upward and repelling itself from the surroundings, and the gravitational force was pointing downward, given that the piece of tape was floating in the air. So these balance one another out in their equal magnitude, which is why I'm able to determine the charge of tape B here, which was 9.8 to the negative 10. And then the number of electrons on tape B was the charge of point charge divided by the charge of protons. The number of atoms on the surface was the tape length times atom diameter, and the fraction of atoms that gave up electrons was around 32%. This is all demonstrated in my modeling within the glow script code. So what if electrons had positive charge and protons had negative charge? The observations would look the exact same because all opposite charges are still attracted to one another. All like charges are still repelling one another. And even though they're different, they're going to look the same to an outsider. The question of why is it important to handle these charge tapes as little as possible? That's because charge is distributed between objects when they interact. So if you handle these objects minimally, they're going to maintain that charge, which is crucial to getting good data for this experiment. In terms of assumptions I made, so I ignored air resistance on a moving object, specifically for the floating piece of tape. I also treated the long piece of tape as though it were a point charge with the charge concentrated at the center of the long tape to make the free body diagram simpler to evaluate. And I also assumed that the U-tape that I had made was about the same charge because that made determining the charge of a specific one a little bit easier. So I demonstrated all of that in my glow script code here. And this is, again, the system of tape piece B and the surroundings of tape piece A. And so like I had mentioned, the magnitude of this gravitational force was around 3.9 to the negative 5 newtons. The charge on the tape B was 9.8 times to the negative 10 coulombs. The corresponding number of electrons on tape B was 6.18 to the 10 to the 9th electrons, and the fraction of atoms that gave up electrons is around 32%. So all of this to say that these pieces of tape were positively charged and that you're able to use household objects to determine charge in these everyday scenarios, and to see these concepts come to life and things that actually affect the way that everyday objects are interacting with each other. So thank you for following along and have a good one.